The universe may look like a peaceful, star-filled expanse stretching endlessly into the night, but it's not what you think, because beneath this serene facade lies a cosmic realm of violence, mystery, and phenomena that challenge everything we thought we knew about reality itself. Welcome to the dark side of existence, where invisible forces tear at the very fabric of space and time, where 95% of everything that exists remains completely hidden from our view, and where the laws of physics break down in ways that would make Einstein himself question his own theories. We live in a universe dominated by dark matter we cannot see, dark energy we cannot understand, and quantum mysteries that suggest our reality might be just one bubble floating in an infinite ocean of parallel worlds. For centuries, we believed we had mapped the cosmos, cataloged the stars, and understood the fundamental forces that govern existence. Now we know better. Advanced telescopes peer into the deepest reaches of space, only to reveal that our universe is stranger, more violent, and more mysterious than we ever dared imagine. Black holes warp space-time into impossible geometries. Stars explode with the force of billions of suns, seeding the cosmos with the very elements that make life possible. Galaxies dance in patterns orchestrated by invisible hands, while quantum particles exist in multiple states simultaneously until the moment we dare to observe them. Tonight, we embark on a journey to confront these cosmic mysteries head-on, armed with humanity's most sophisticated instruments and guided by our most brilliant minds. From the subatomic realm, where reality itself becomes uncertain, to the largest structures in the observable universe, we'll explore the phenomena that keep scientists awake at night and challenge our most fundamental assumptions about existence. This is our quest to understand the universe's deepest secrets, to peer beyond the visible horizon of knowledge, and to discover what lies hidden in the cosmic shadows. Join the Sleep Lab as we dive deep into the mysteries that define our universe, and perhaps in the process, discover what it truly means to exist in such an extraordinary cosmos. 1 Cape Canaveral, Florida. Dawn breaks over the horizon as humanity's latest attempt to decode the universe's deepest secrets prepares for launch. Tucked inside the nose cone of a towering rocket sits an instrument that represents decades of human ingenuity and our relentless quest to understand the invisible forces that govern reality itself. This is not just another space mission. This is our species' most ambitious hunt for answers to questions that have haunted us since we first looked up at the stars and wondered what lies beyond the visible realm of existence. The mission launching today carries the Cosmic Dark Matter Observatory, a revolutionary telescope designed to detect the signatures of particles that make up what scientists believe is the majority of all matter in the universe, yet remains completely invisible to every instrument we've ever built. As the countdown reaches its final moments, scientists around the world hold their breath. This launch represents more than technological achievement. It represents humanity's refusal to accept ignorance about our own cosmic home. How do you hunt for something that by its very nature cannot be seen, cannot be touched, and barely interacts with anything we understand as normal matter? This is the challenge that has driven a new generation of cosmic detectives to push the boundaries of human knowledge further than ever before. They are not searching for distant galaxies or exotic stars. They are hunting for the invisible scaffolding upon which our entire universe is built, the mysterious dark matter that outweighs everything we can see by a ratio of 5-to-1. Dr. Elena Rodriguez has spent the last 15 years of her life preparing for this moment. As the mission's lead scientist, she represents a growing community of researchers who have dedicated their careers to solving what many consider the greatest mystery in modern physics. Standing in the Mission Control Center, watching telemetry data stream across dozens of monitors, she knows that success today could revolutionize our understanding of reality itself. Failure would mean waiting another decade for the next opportunity to peer into the cosmic shadows. We're essentially trying to weigh the invisible, Dr. Rodriguez explains, her eyes fixed on the launch pad, visible through the control room's massive windows. Imagine trying to understand a city by only being able to see 1 in 20 buildings. That's what we're dealing with when we study the universe. Everything we can observe directly, every star, every planet, every galaxy, represents just a tiny fraction of what actually exists out there. The rocket engines ignite with a thunderous roar that shakes the ground for miles around. As the spacecraft climbs through Earth's atmosphere, it carries with it humanity's hopes of finally understanding the true architecture of the cosmos. But this is just one mission in a global effort that spans continents and involves thousands of the world's brightest minds, all united by a common goal: to solve the mysteries that make our universe possible. 300 feet beneath the surface of an abandoned mine in South Dakota, another team of scientists wages their own war against cosmic ignorance. The Sanford Underground Research Facility represents one of the most ambitious attempts ever made to detect dark matter particles directly. Here, shielded from cosmic rays and electromagnetic interference by layers of rock that took millions of years to form, ultra-sensitive detectors wait in perfect silence for the telltale signature of a dark matter particle colliding with ordinary matter. Dr. Marcus Chen, the facility's director, leads visitors through a maze of tunnels carved from solid rock. The air is cool and perfectly still, broken only by the distant hum of machinery and the soft footsteps of researchers making their rounds. "Down here, we're trying to catch ghost particles," he says, his voice echoing off the tunnel walls. Dark matter particles are streaming through your body right now, billions of them every second, and you feel absolutely nothing. They pass through solid rock as if it weren't there. But very occasionally, perhaps once in a trillion interactions, one of these particles will collide with an atomic nucleus in our detectors. The detectors themselves are marvels of engineering, cooled to temperatures colder than the vacuum of space and isolated from every possible source of interference. They consist of tanks filled with liquid xenon, one of the heaviest stable elements, chosen specifically because its massive atomic nuclei provide the best possible target for elusive dark matter particles. When a collision occurs, it releases a tiny flash of light and a small electrical signal, evidence of an interaction with matter that exists in a shadow realm beyond our normal perception. But the hunt for cosmic mysteries extends far beyond dark matter. At the South Pole, where the ice is 2 miles thick and the sky remains dark for months at a time, another team of scientists has built what they call a neutrino telescope deep within the frozen landscape. The Ice Cube Neutrino Observatory represents a fundamental shift in how we explore the universe. Instead of looking up at the sky, these researchers are looking down through the entire planet, using the Earth itself as a shield to filter out unwanted particles while allowing neutrinos, nearly massless particles that can travel through almost anything, to pass through unimpeded. Dr. Sarah Winters bundles herself in layers of insulation before stepping outside the research station. The temperature is 40 degrees below zero, and the wind cuts through even the best protective gear like a knife made of ice. But the harsh conditions are exactly what makes this location perfect for cosmic research. Neutrinos are produced in the most violent events in the universe, she explains, her breath forming ice crystals that fall immediately to the ground. When stars explode in supernovas, when black holes tear apart entire solar systems, when cosmic rays from distant galaxies collide with our atmosphere, all of these events produce neutrinos that carry information about processes we could never observe any other way. The ice cube detector consists of thousands of light sensors buried in holes melted through the Antarctic ice sheet. When a neutrino interacts with water molecules in the ice, it produces a flash of blue light that travels through the frozen medium faster than light can travel through ice, a phenomenon known as Cherenkov radiation. By tracking these flashes of light from multiple sensors, scientists can reconstruct the path of the neutrino and trace it back to its cosmic origin, essentially using individual particles as messengers from the most extreme environments in the universe. Each detection represents a triumph of human ingenuity over cosmic indifference. Neutrinos are so weakly interactive that trillions pass through every square centimeter of your body every second without you ever knowing they exist. To catch even one requires detectors the size of skyscrapers and patience measured in years. Yet when detection occurs, it opens a window into cosmic processes that would otherwise remain forever hidden behind veils of gas, dust, and the fundamental limitations of electromagnetic radiation. Meanwhile, in orbit high above Earth's atmosphere, the James Webb Space Telescope continues its mission to peer deeper into space and further back in time than any human instrument has ever achieved. Unlike its predecessors, which observed the universe primarily in visible light, Webb sees the cosmos in infrared radiation, heat signatures that reveal processes invisible to human eyes. Its 18 gold-plated mirror segments work together to collect photons that began their journey across the universe when the first stars were being born, carrying information about cosmic conditions from an era when the universe itself was still in its infancy. Dr. Rachel Kim, an astrophysicist at the Space Telescope Science Institute, spends her days analyzing data that arrives from Webb at a rate of nearly 200 gigabytes per day. Each image represents thousands of hours of observation time and contains information that could potentially rewrite our understanding of cosmic evolution. We're seeing galaxies that formed when the universe was less than 400 million years old, she explains, while examining a computer screen filled with red and orange points of light against the black backdrop of space. These are not the kinds of galaxies we expected to find. They're too massive, too organized, too mature for such an early cosmic epoch. The unexpected discovery of these early massive galaxies represents exactly the kind of mystery that drives cosmic research forward. According to our current models of universe formation, galaxies should have grown slowly from small clumps of matter that gradually attracted more material through gravitational attraction. The process should have taken billions of years, yet Webb's observation suggests that some galaxies achieved enormous size and complexity in a fraction of that time, challenging fundamental assumptions about how cosmic structures form and evolve. Every new observation raises more questions than it answers. How did these early galaxies become so massive so quickly? What processes were operating in the young universe that we haven't accounted for in our models? Are there aspects of gravity, dark matter, or cosmic evolution that we fundamentally misunderstand? These are the kinds of questions that keep researchers working through the night, analyzing data, running simulations, and developing new theories to explain observations that don't fit existing paradigms. The hunt for answers extends beyond individual missions and facilities to encompass a global network of researchers who share data, collaborate on theories, and challenge each other's assumptions in the pursuit of cosmic truth. At research universities around the world, graduate students and postdocs work alongside senior scientists to develop new mathematical models that might explain mysterious observations. Computer simulations run for months at a time, modeling the evolution of the universe from the Big Bang to the present day, testing whether our current understanding of physics can account for the structures and phenomena we observe. Dr. Ahmed Hassan leads one of these computational efforts at a major research university, overseeing simulations that require some of the world's most powerful supercomputers. His team's latest simulation models the behavior of dark matter over 13 billion years of cosmic history, tracking how invisible particles clump together under their own gravity to form the scaffolding upon which galaxies would eventually form. The simulation contains over 1 trillion particles and takes months to complete, even on machines capable of performing quadrillions of calculations per second. The universe is not just stranger than we imagine, Dr. Hassan reflects, while watching visualization software render the results of his team's latest simulation. It's stranger than we can imagine. Every time we think we figured something out, nature reveals another layer of complexity that we never suspected existed. Dark matter, dark energy, quantum mechanics, the multiverse. Each of these concepts challenges our most basic assumptions about reality. The visualization shows the cosmic web, a vast network of filaments made of dark matter that spans billions of light years and connects galaxy clusters across the observable universe. It resembles a three-dimensional spider web, with dense nodes where galaxies form and vast empty spaces called cosmic voids, where almost nothing exists. This structure emerged from tiny fluctuations in the density of matter during the universe's first moments, growing over billions of years through gravitational attraction into the largest organized structures known to exist. But even these massive simulations can only model what we think we understand. The true mystery lies in what we don't yet know, the processes, particles, and forces that might exist beyond our current theories. Dark energy, the mysterious force that appears to be accelerating the expansion of the universe, remains completely unexplained by any known physics. Quantum mechanics suggests that reality at the smallest scales behaves in ways that seem to violate common sense, with particles existing in multiple states simultaneously and becoming entangled across vast distances in ways that Einstein famously called spooky action at a distance. Recent experiments in quantum physics have pushed these mysterious behaviors to increasingly large scales, suggesting that the strange rules governing subatomic particles might apply to bigger systems than we ever imagined possible. Laboratory experiments have demonstrated quantum entanglement between particles separated by hundreds of kilometers, quantum superposition in objects containing trillions of atoms, and quantum tunneling effects that allow particles to pass through barriers that should be impenetrable according to classical physics. Dr. Lisa Park, a quantum physicist at a leading research institution, has spent the last decade exploring the boundary between quantum mechanics and everyday reality. Her laboratory contains some of the most sophisticated quantum control systems ever built, capable of manipulating individual atoms with laser light and maintaining quantum states for increasingly long periods of time. The quantum world doesn't just exist at microscopic scales, she explains, while adjusting the alignment of mirrors in a laser system that fills an entire room. Quantum effects are everywhere. They determine how stars burn, how atoms bond to form molecules, how plants capture sunlight, and how your brain processes information. The implications extend far beyond academic curiosity. Understanding quantum mechanics has already led to revolutionary technologies, including lasers, MRI machines, computer processors, and GPS satellites. Current research into quantum computing and quantum communication promises to enable calculations that are impossible with conventional technology and communication systems that are fundamentally secure against eavesdropping. But perhaps most importantly, quantum mechanics provides clues about the deep structure of reality itself. The mathematical rules that govern everything from subatomic particles to the largest structures in the universe. As night falls over research facilities around the world, the hunt for cosmic answers continues. Radio telescopes track across the sky, recording signals from pulsars whose precision rivals atomic clocks and whose magnetic fields are trillions of times stronger than anything achievable on Earth. Gravitational wave detectors listen for ripples in spacetime itself, caused by the collisions of black holes and neutron stars billions of light years away. Particle accelerators smash protons together at nearly the speed of light, recreating conditions that existed microseconds after the Big Bang, and searching for new forms of matter that might explain the universe's hidden sectors. Each detection, each measurement, each unexpected result adds another piece to a cosmic puzzle that grows more complex with every advance in our understanding. We have learned that the universe is far stranger, more violent, and more mysterious than our ancestors ever imagined. We live in a cosmos dominated by invisible matter and driven by unknown energy, where space and time themselves can be stretched, compressed, and torn apart by gravitational forces beyond human comprehension. The hunt for answers drives us forward not just because of scientific curiosity, but because understanding our cosmic environment is fundamentally important for understanding ourselves. We are made of elements forged in the nuclear furnaces of ancient stars. Our planet orbits one star among hundreds of billions in a galaxy that is itself just one of trillions scattered across an observable universe that may be only a tiny fraction of a much larger cosmic reality. Every photon of light that reaches our telescopes, every cosmic ray that strikes our atmosphere, every neutrino that passes through our detectors carries information about processes and environments that exist at the very limits of physical possibility. Black holes where gravity is so strong that time itself slows to a crawl. Neutron stars where a teaspoon of matter weighs as much as a mountain. Cosmic voids so empty that galaxies are separated by distances that light takes hundreds of millions of years to cross. As dawn approaches over observatories around the world, researchers continue their patient vigil, waiting for the next detection, the next measurement, the next unexpected discovery that might illuminate another aspect of cosmic reality. They know that each mystery solved will likely reveal 10 new questions. They understand that the universe guards its secrets jealously, and reveals them only to those willing to push the boundaries of human knowledge into previously unexplored territories. The hunt for answers is more than a scientific endeavor. It is an expression of the human spirit itself. Our refusal to accept ignorance about the universe that created us, our determination to understand the cosmic forces that govern our existence, and our willingness to dedicate our brief lives to expanding the boundaries of human knowledge for the benefit of future generations who will continue this quest long after we are gone. In laboratories buried deep underground, on mountaintops where the air is thin and the sky is dark, in the vacuum of space where telescopes peer across billions of light years, the hunt continues. We are cosmic detectives armed with instruments of incredible sophistication, following clues that lead us deeper into the mystery of existence itself. And with each discovery, each breakthrough, each moment of understanding, we come closer to answering the fundamental questions that have driven human curiosity since we first developed the capacity to wonder. What is the universe made of? How did it begin? Where is it going? And what does it all mean for us? Temporary arrangements of cosmic matter that have somehow developed the ability to contemplate our own existence and seek answers to questions that may be as infinite as the universe itself. To now, we are moving to the next part of the documentary. Having explored the current scientific endeavors that drive our hunt for cosmic answers, we must now delve deeper into the theoretical foundations that make these mysteries possible. The strange principles of physics that govern our universe are not merely abstract concepts confined to textbooks. They are the invisible architects of reality itself, shaping everything from the smallest quantum particles to the largest structures spanning billions of light years across the cosmic web. The foundation of mystery. Albert Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible at all. Yet as we delve deeper into the cosmic mysteries that surround us, we discover that comprehension itself rests upon foundations far stranger and more mysterious than Einstein himself could have imagined when he revolutionized our understanding of space, time, and gravity over a century ago. To truly hunt for the universe's deepest secrets, we must first understand the bizarre scientific principles that make these mysteries possible. Principles that challenge every intuitive notion we have about the nature of reality itself. The story begins with Einstein's most famous equation, E equals mc squared, which revealed that matter and energy are interchangeable manifestations of the same fundamental reality. But this seemingly simple relationship opened the door to a universe far more complex and mysterious than anyone had previously suspected. When Einstein published his theory of general relativity in 1915, he provided humanity with a new way of understanding gravity, not as a mysterious force pulling objects together, but as the curvature of space-time itself caused by the presence of matter and energy. Imagine, if you will, a stretched rubber sheet representing the fabric of space-time. Place a heavy bowling ball in the center, and the sheet will curve and warp around it. Now roll marbles across the sheet, and they will follow curved paths around the bowling ball, not because any force is pulling them, but because they are simply following the geometry of the curved surface. This is Einstein's revolutionary insight. Massive objects don't pull on other objects through some mysterious gravitational force. Instead, they warp the very geometry of space and time, and objects simply follow the straightest possible paths through this curved space-time. But Einstein's geometric revolution was just the beginning. His equations predicted phenomena so bizarre that even he initially doubted their reality. Black holes, regions where space-time curvature becomes so extreme that not even light can escape, seem too strange to exist. Gravitational waves, ripples in the fabric of space-time itself traveling at the speed of light, appeared to be purely theoretical constructs with no hope of detection. Time dilation, the slowing of time in strong gravitational fields, violated every human intuition about the absolute nature of temporal flow. Dr. Kip Thorne, the Nobel Prize-winning physicist whose theoretical work laid the foundation for detecting gravitational waves, spent decades developing the mathematical framework needed to understand these space-time distortions. Standing in his office at Caltech, surrounded by blackboards covered with equations that describe the behavior of warped space-time, he reflects on the strange universe that Einstein's mathematics revealed. When we first began to understand what general relativity was telling us about the nature of reality, it seemed almost impossible to believe. Dr. Thorne explains, while gesturing toward equations that describe how massive spinning objects can literally drag space-time around with them like honey. Einstein's equations predicted that when two black holes spiral into each other and merge, they should create ripples in space-time that spread outward at the speed of light, stretching and compressing space itself as they pass. The effect is incredibly tiny. By the time these gravitational waves reach Earth from distant cosmic collisions, they stretch space by less than 1/10,000th the width of a proton. Detecting such minuscule distortions requires instruments more sensitive than anything humanity had ever built. The Laser Interferometer, Gravitational Wave Observatory, known as LIGO, represents one of the most ambitious attempts ever made to test Einstein's most exotic predictions. The facility consists of two identical detectors, one in Louisiana and one in Washington state, each containing laser interferometers with arms extending 4 kilometers in perpendicular directions. Laser light bounces back and forth between mirrors suspended in perfect vacuum, and when a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the other, changing the length of the laser paths by amounts smaller than 1/10,000th the width of a proton. Dr. Gabriela Gonzalez, a physicist who has devoted her career to gravitational wave astronomy, remembers the moment when LIGO first detected these space-time ripples on September 14th, 2015. I was looking at the data on my computer screen, and I could see this distinctive chirp pattern, the signature of two black holes spiraling into each other and merging about 1.3 billion light-years away from Earth. For just a moment, I doubted what I was seeing because it seemed almost too perfect, too much like the theoretical predictions we had been working with for decades. That first detection confirmed one of Einstein's most extraordinary predictions and opened an entirely new window into the universe's most violent and mysterious phenomena. Since then, gravitational wave detectors have observed dozens of black hole mergers, collisions between neutron stars, and other cosmic events that were previously invisible to all forms of electromagnetic observation. Each detection provides direct evidence that space-time itself is a dynamic, malleable medium that can be stretched, compressed, twisted, and torn by the universe's most extreme gravitational fields. But gravitational waves represent just one aspect of the mysterious foundation upon which cosmic reality rests. To understand the deeper mysteries of dark matter and dark energy, we must venture into the strange realm of quantum mechanics, where the very concept of definite properties breaks down, and reality itself becomes fundamentally probabilistic rather than deterministic. Quantum mechanics emerged in the early 20th century from attempts to understand the behavior of atoms and the emission of light by hot objects. What scientists discovered challenged every assumption about the nature of physical reality. At the quantum scale, particles don't have definite positions or velocities until they are measured. Instead, they exist in what physicists call superposition, a state where they simultaneously possess all possible values of a property until an observation forces them to collapse into a single definite state. Dr. Wojciech Zurek, a theoretical physicist at Los Alamos National Laboratory, has spent his career trying to understand how the strange rules of quantum mechanics give rise to the classical reality we experience in everyday life. His office walls are covered with diagrams showing the mathematical relationships between quantum superposition, measurement, and the emergence of classical behavior in large systems. The quantum world is not just different from our everyday experience, Dr. Zurek explains, while sketching wave functions on a whiteboard. It's so fundamentally different that we don't even have adequate language to describe it without using mathematical formalism. Consider the famous thought experiment of Schrödinger's cat, which illustrates the paradox of quantum superposition. According to quantum mechanics, a radioactive atom exists in a superposition of decayed and non-decayed states until it is observed. If we connect a Geiger counter to the atom and use it to trigger a mechanism that either releases poison or leaves a cat alive, then the cat itself should exist in a superposition of alive and dead states until someone opens the box to observe it. This seems absurd, but it follows logically from the fundamental principles of quantum mechanics. The resolution of this paradox lies in understanding how quantum systems interact with their environment through a process called decoherence. When quantum particles interact with large numbers of other particles in their surroundings, they lose their quantum coherence and behave more like classical objects with definite properties. This process happens extremely rapidly for large objects, which is why we don't observe quantum superposition in everyday life. But it preserves quantum behavior for small, isolated systems under carefully controlled conditions. Recent experiments have pushed quantum superposition to increasingly large scales, demonstrating quantum effects in systems containing millions or even billions of atoms. Researchers have created quantum superposition states in microscopic diamonds, biological molecules, and even small mechanical oscillators visible to the naked eye. These experiments suggest that the boundary between quantum and classical reality is not fixed, but depends on the degree of isolation from environmental influences. The implications extend far beyond laboratory curiosities. Quantum mechanics appears to be fundamental to understanding how the universe evolved from its earliest moments. During cosmic inflation, the rapid expansion of space that occurred in the first fraction of a second after the Big Bang, quantum fluctuations in energy density were stretched to cosmic scales and became the seeds from which galaxies and other large-scale structures eventually grew. The cosmic microwave background radiation that fills the universe today carries the imprint of these primordial quantum fluctuations, providing direct observational evidence that quantum mechanics operated on cosmic scales during the universe's infancy. But perhaps the most mysterious aspect of quantum mechanics is the phenomenon of entanglement, where particles become connected in such a way that measuring one instantaneously affects the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance and argued that it proved quantum mechanics must be incomplete. However, decades of experimental tests have confirmed that entanglement is real and that the universe does indeed allow for instantaneous correlations across arbitrary distances. Dr. Anton Zeilinger, a quantum physicist at the University of Vienna, whose experiments have demonstrated quantum entanglement across hundreds of kilometers, reflects on the philosophical implications of these strange quantum connections. Entanglement forces us to abandon our classical notions of locality and realism, he explains, while showing visitors through a laboratory filled with lasers, mirrors, and single-photon detectors. We must accept that the properties of quantum particles are not determined locally, and that measurement outcomes can be influenced by events occurring at distant locations faster than light could travel between them. Recent experiments have extended quantum entanglement from individual particles to larger systems, including small mechanical oscillators and even biological molecules. Some researchers speculate that quantum entanglement might play a role in biological processes such as photosynthesis, bird navigation, and possibly even consciousness itself. While these ideas remain highly speculative, they suggest that quantum mechanics might be far more important for understanding the nature of life and mind than previously suspected. The strange properties of quantum mechanics become even more mysterious when combined with Einstein's relativity. According to quantum field theory, the mathematical framework that unifies quantum mechanics with special relativity, empty space is not actually empty, but filled with quantum fluctuations. Virtual particles that pop into existence for brief moments before annihilating each other. These quantum vacuum fluctuations have measurable effects, including the Casimir force that pushes parallel metal plates together, and the Lamb shift that slightly alters the energy levels of hydrogen atoms. But the most profound mystery emerges when we try to combine quantum mechanics with general relativity to understand what happens at the smallest scales of space and time, at distances smaller than the Planck length, about 10 to the negative 35th meters, and time shorter than the Planck time, about 10 to the negative 43rd seconds. The normal concepts of space and time break down completely. At these scales, quantum fluctuations in space-time itself become so large that the very geometry of space and time becomes uncertain and probabilistic. Dr. Lee Smolin, a theoretical physicist at the Perimeter Institute for Theoretical Physics, has devoted his career to developing new approaches to quantum gravity that might resolve this fundamental tension between our two most successful theories of physics. His office contains shelves lined with books on topics ranging from loop quantum gravity to emergent space-time, representing decades of attempts to understand how quantum mechanics and general relativity might be unified into a single theoretical framework. The problem we face is that quantum mechanics and general relativity make fundamentally different assumptions about the nature of space and time. Dr. Smolin explains, while drawing diagrams that illustrate how space-time might be composed of discrete quantum units at the smallest scales. Quantum mechanics assumes that space and time form a fixed background against which quantum processes occur. General relativity tells us that space and time are dynamical entities that can be curved, stretched, and distorted by matter and energy. When we try to combine these approaches at very small scales, we get mathematical inconsistencies that suggest our current understanding is incomplete. Various approaches to quantum gravity propose radically different solutions to this problem. String theory suggests that the fundamental constituents of matter are not point particles, but tiny vibrating strings existing in 10 or 11 dimensions, most of which are curled up so small that we can't observe them directly. Loop quantum gravity proposes that space itself is quantized into discrete units, like pixels in a digital image, at the smallest possible scales. Emergent gravity theories suggest that space-time itself might be an emergent property arising from more fundamental quantum information processes. Each of these approaches leads to different predictions about the nature of black holes, the behavior of space-time near the Big Bang, and the possibility of parallel universes or multiple dimensions. Some theories suggest that black holes might be connected to other regions of space-time through wormholes, hypothetical tunnels that could theoretically allow travel across vast distances or even to other universes. Others propose that the information that falls into black holes is somehow preserved and eventually released through quantum processes that operate over cosmological timescales. The search for experimental tests of these ideas pushes the boundaries of current technology. Particle accelerators attempt to recreate the extreme energy densities that existed moments after the Big Bang, looking for evidence of extra dimensions or new forms of matter predicted by various quantum gravity theories. Astronomical observations search for subtle effects that might reveal the quantized structure of space-time or the existence of parallel universes that could interact with our own through gravitational effects. But perhaps the most mysterious foundation underlying cosmic reality is the role of information itself. Recent developments in theoretical physics suggest that information might be more fundamental than matter, energy, space, or time. The holographic principle, developed from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on the surface that bounds that volume, like a hologram that contains three-dimensional information in a two-dimensional medium. Dr. Leonard Susskind, a theoretical physicist at Stanford University who helped develop the holographic principle, argues that this insight fundamentally changes our understanding of reality. We used to think that information was something that described physical systems, he explains, while writing equations on a blackboard that describe how quantum information is encoded in the structure of space-time. Now, we're beginning to suspect that information might be the fundamental ingredient from which physical systems are constructed. Matter, energy, space, and time might all be emergent properties of underlying information processing systems. This perspective suggests that the universe itself might be understood as a vast quantum computer, processing information according to the laws of quantum mechanics and general relativity. Black holes become information processors that scramble and eventually return information through quantum mechanical processes. The expansion of the universe becomes a process of increasing the total information storage capacity of cosmic space. Even consciousness and life might be understood as particularly complex forms of information processing that emerge from the underlying quantum computational substrate of reality. Recent experiments in quantum information science have demonstrated some of the strange properties that would be expected if information is indeed fundamental to physical reality. Quantum teleportation allows the complete information describing a quantum particle to be transferred from one location to another, without the particle itself traveling through the intervening space. Quantum error correction shows how quantum information can be protected from decoherence by encoding it in entangled states distributed across multiple particles. Quantum algorithms demonstrate computational capabilities that exceed anything possible with classical information processing. As we push deeper into understanding the foundations of cosmic mystery, we discover that reality is constructed from principles that challenge our most basic intuitions about the nature of existence. Space and time are not fixed stages upon which physical processes occur, but dynamic entities that can be stretched, compressed, and torn by gravitational forces. Matter and energy are interchangeable forms of the same underlying reality, governed by quantum mechanical rules that allow particles to exist in multiple states simultaneously and become entangled across arbitrary distances. The implications extend far beyond abstract theoretical physics. Understanding these foundational mysteries is essential for developing the technologies that will allow us to probe deeper into cosmic reality. Gravitational wave detectors rely on our understanding of how spacetime responds to extreme gravitational fields. Quantum computers harness the strange properties of superposition and entanglement to solve problems that are intractable for classical machines. Dark matter detection experiments depend on our understanding of how exotic particles might interact with ordinary matter through quantum mechanical processes. But perhaps most importantly, these foundational mysteries remind us that the universe is far stranger and more wonderful than we could have imagined from our everyday experience. The cosmic reality revealed by modern physics is a place where the flow of time can slow to a crawl in strong gravitational fields, where particles can tunnel through barriers that should be impenetrable, where the vacuum of space seethes with quantum fluctuations that have measurable effects on physical systems. As we continue our hunt for cosmic answers, we must always remember that the mysteries we seek to solve rest upon foundations that are themselves deeply mysterious. Every detection, every measurement, every theoretical breakthrough reveals new layers of complexity and raises fresh questions about the ultimate nature of reality. We are cosmic archaeologists, carefully excavating the mathematical structures that underlie physical existence, guided by theoretical frameworks that push the boundaries of human comprehension and experimental techniques that test the limits of what is measurable and observable. The foundation of mystery upon which our cosmic understanding rests is not a weakness in our knowledge, but a source of endless wonder and discovery. It reminds us that the universe is under no obligation to conform to our expectations or to reveal its secrets easily. Every answer we uncover leads to deeper questions. Every solved mystery opens doors to new realms of investigation, and every theoretical breakthrough reveals the vast expanses of cosmic reality that remain to be explored. In this ongoing quest to understand the foundational principles that make cosmic mysteries possible, we participate in one of humanity's greatest adventures, the attempt to comprehend a universe that is stranger, more beautiful, and more profound than our ancestors ever dared to dream. Now, we are moving to the next part of the documentary, where we journey back in time to witness the universe's most dramatic transformation, from a hot, uniform sea of particles to the first luminous beacons that pierce the cosmic darkness. This is the story of how gravity sculpted chaos into order, how the first stars ignited nuclear furnaces that would forge the elements of life itself, and how the universe began its long journey toward complexity. Segment 3. birth of the cosmic architects. 13 billion years ago, the universe was a very different place. There were no stars lighting up the cosmic darkness, no galaxies spinning through space, no planets harboring life. Instead, the cosmos existed in what astronomers call the Dark Ages, a period when the universe was filled with a nearly uniform fog of hydrogen and helium gas, heated to thousands of degrees, but gradually cooling as space itself expanded and stretched the fabric of reality. This primordial soup contained the seeds of everything we see today, but those seeds were incredibly subtle. Tiny fluctuations in density that amounted to variations of just 1 part in 100,000. Yet these microscopic ripples in the cosmic fabric would eventually grow under the relentless pull of gravity into the largest structures in the universe. Understanding how this transformation occurred requires us to peer into one of the most mysterious chapters in cosmic history, a time when the first stars were born and began the process of chemical evolution that would make planets, life, and consciousness possible. Dr. Volker Braun stands before a wall-sized display showing the results of one of the most ambitious computer simulations ever attempted, a model that traces the formation of the first stars from the primordial conditions that existed just a few 100 million years after the Big Bang. His team at the University of Texas has spent years developing the computational tools needed to follow this process, tracking how tiny density fluctuations grew into the massive gas clouds that would collapse to form the universe's first generation of stars. The first stars were unlike anything we see in the universe today, Dr. Braun explains, while manipulating the three-dimensional visualization that shows how primordial gas clouds evolved over millions of years. These population 3 stars, as we call them, formed from gas that was almost perfectly pure, just hydrogen and helium with trace amounts of lithium. They had no heavy elements, no carbon, no oxygen, no silicon. This pristine composition allowed them to grow to enormous sizes, perhaps 100 times more massive than our sun. The simulation reveals a process of extraordinary violence and beauty. As the universe expanded and cooled, dark matter, the invisible scaffolding that outweighs ordinary matter by a factor of 5, began to clump together under its own gravitational attraction. These dark matter halos created gravitational wells that attracted the surrounding hydrogen and helium gas, causing it to fall inward and heat up through compression. When the gas reached sufficient density and temperature, nuclear fusion ignited, and the first stars blazed to life. But these primordial giants lived fast and died young. Without heavy elements to help radiate away excess heat, they burned their nuclear fuel at prodigious rates, exhausting their hydrogen in just a few million years. A blink of an eye compared to the 10 billion year lifetime expected for a star like our sun. When their fuel ran out, they collapsed catastrophically, triggering supernova explosions of unimaginable power that scattered the first heavy elements throughout the surrounding gas clouds. Dr. Anna Friebel, a stellar archaeologist at MIT, has devoted her career to finding the ancient survivors of this early epoch, stars that formed from gas clouds enriched by the explosions of the very first stellar generation. Her work involves scanning thousands of faint stars in the outer regions of our galaxy, searching for the chemical signatures that reveal their ancient origins. These stars are like fossils, she explains, while examining spectra that show the light from distant stars broken down into its component wavelengths. Their atmospheric compositions preserve a record of the chemical enrichment that occurred when the first generation of stars died and spread their ashes throughout the early universe. The search for these stellar fossils has revealed surprising insights about the nature of the first stars and their explosive deaths. Some ancient stars show evidence of being enriched by supernovas that produced unusual ratios of heavy elements, suggesting that the first stellar explosions were different from the supernovas we observe today. Others contain elements that can only be produced in the most energetic stellar explosions, providing clues about the masses and death mechanisms of the universe's first generation of stars. But the story of cosmic origins extends far beyond individual stars to encompass the formation of the first galaxies. Gravitationally bound collections of stars, gas, and dark matter that would become the basic building blocks of large-scale cosmic structure. Dr. Michael Norman, a computational astrophysicist at UC San Diego, has developed some of the most sophisticated simulations of early galaxy formation, tracking how the first stars influence the evolution of their host galaxies and the surrounding intergalactic medium. The first stars didn't just enrich their surroundings with heavy elements, Dr. Norman explains, while showing animations that reveal the complex feedback processes governing early galaxy evolution. They also produced intense ultraviolet radiation that ionized the surrounding hydrogen gas, fundamentally changing the thermal state of the early universe. This process, called cosmic reionization, transformed the universe from a neutral medium to an ionized plasma, allowing light to travel freely through space for the first time since the cosmic microwave background was emitted. The reionization of the universe represents one of the most dramatic phase transitions in cosmic history, comparable to the moment when the cosmic microwave background was released and the universe became transparent to light for the first time. But unlike that earlier epoch, which occurred uniformly throughout space, reionization was a patchy, chaotic process driven by the uneven distribution of the first stars and galaxies. Some regions were ionized early by nearby stellar sources, while others remained neutral until much later times. Understanding reionization requires combining theoretical models with observations from the most powerful telescopes ever built. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, can observe galaxies that formed when the universe was less than 5% of its current age. These observations reveal that early galaxies were surprisingly diverse, with some showing signs of active star formation, while others appear to have already assembled substantial stellar populations. Dr. Brant Robertson, an astronomer at UC Santa Cruz, who analyzes Webb's observations of high redshift galaxies, describes the challenge of interpreting these ancient light signals. When we look at a galaxy that formed 13 billion years ago, we're seeing light that has been traveling through the expanding universe for most of cosmic history. The wavelengths have been stretched by the expansion of space itself, shifting visible light into the infrared and making these objects appear much redder than they would if observed nearby. The observations reveal galaxies that are both smaller and more active than their modern counterparts. Many show intense bursts of star formation, creating new stars at rates hundreds of times higher than the current rate in our own Milky Way. This vigorous stellar production was fueled by the copious amounts of pristine gas available in the early universe, before stellar winds and supernova explosions had blown much of this material out of galaxy centers. But perhaps the most surprising discovery has been the detection of supermassive black holes in some of these early galaxies, objects containing millions or billions of times the mass of our Sun, existing when the universe was less than 1 billion years old. These observations pose a fundamental challenge to our understanding of black hole formation and growth, since conventional models suggest that such massive objects should take much longer to assemble. Dr. Priyamvada Natarajan, a theoretical astrophysicist at Yale University who studies black hole formation in the early universe, has proposed novel mechanisms that might explain these observations. The problem is that if you start with stellar mass black holes formed from the first generation of stars, and they grow by accreting surrounding gas, it's very difficult to reach supermassive scales in the time available, she explains, while sketching diagrams that illustrate different black hole formation pathways. One possibility is that some black holes form directly from the collapse of massive gas clouds, bypassing the stellar formation stage entirely. Another is that dense clusters of the first stars underwent runaway mergers, creating intermediate mass black holes that could serve as seeds for more rapid growth. These scenarios predict different observational signatures that we're now trying to detect with current and future telescopes. The quest to understand supermassive black hole formation has led to increasingly sophisticated simulations that model the complex interplay between star formation, black hole growth, and galaxy evolution in the early universe. These simulations reveal that the formation of the first supermassive black holes was intimately connected to the assembly of the first galaxies, with feedback processes linking stellar and black hole formation in ways that are only beginning to be understood. As the first billion years of cosmic history unfolded, the universe underwent a dramatic transformation. The pristine simplicity of the post-Big Bang era gave way to increasing chemical complexity as successive generations of stars lived and died, each contributing new elements to the growing inventory of heavy elements available for planet formation. Hydrogen and helium, which initially comprised more than 99.9% of all ordinary matter, were gradually supplemented by carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements created in stellar cores and supernova explosions. Dr. Ken Nomoto, a theoretical astrophysicist at the University of Tokyo who studies stellar nucleosynthesis, has mapped out the complex network of nuclear reactions that occur inside stars and during their explosive deaths. Each type of star contributes different elements to the cosmic inventory. He explains, while showing charts that trace the production of specific elements through different stellar evolution pathways. Low-mass stars like our Sun produce carbon and nitrogen through helium burning in their cores. Massive stars create oxygen, silicon, and iron through successive stages of nuclear fusion. The most massive stars end their lives in core collapse supernovas that forge elements heavier than iron through rapid neutron capture processes. This chemical evolution was not uniform throughout the universe. Galaxies with vigorous star formation enriched their gas supplies more rapidly, while smaller systems with lower star formation rates retained more primitive compositions for longer periods. The process was further complicated by galactic winds driven by stellar feedback, which could blow chemically enriched gas out of galaxy centers and distribute it throughout the surrounding intergalactic medium. The observational evidence for this chemical evolution comes from studying the compositions of stars of different ages and metallicities. The oldest stars in our galaxy show compositions that are almost entirely hydrogen and helium, with heavy element abundances that are thousands of times lower than in the Sun. Younger stars show progressively higher heavy element contents, reflecting the gradual enrichment of the interstellar medium through successive generations of stellar death and rebirth. But the story of cosmic chemical evolution is not just about the production of heavy elements. It's also about their distribution and incorporation into new generations of stars and planetary systems. Dr. Crystal Martin, an astronomer at UC Santa Barbara who studies galactic outflows, has used observations from space-based telescopes to trace how supernova explosions and stellar winds transport heavy elements from their stellar birthplaces into the wider galaxy and beyond. The metals produced in stellar cores don't just sit there, Dr. Martin explains, while showing images of nearby galaxies that reveal extensive outflows of gas enriched with heavy elements. Stellar winds and supernova explosions create hot, expanding bubbles of gas that can travel thousands of light years from their sources. In some cases, these outflows are so energetic that they completely escape the gravitational pull of their host galaxies, enriching the intergalactic medium with heavy elements that can later be incorporated into new galaxy formation events. These metal-enriched outflows represent a crucial component of cosmic evolution, redistributing the products of stellar nucleosynthesis on galactic and intergalactic scales. Computer simulations that track the flow of baryonic matter through cosmic time reveal complex patterns of enrichment, with some regions receiving multiple generations of stellar ejecta, while others remain relatively pristine for billions of years. The transition from the first generation of metal-free stars to the second generation of metal-enriched stars marks a fundamental turning point in cosmic evolution. Once, even small amounts of heavy elements were present in star-forming gas clouds, the physics of stellar formation changed dramatically. Heavy elements provide efficient cooling mechanisms that allow gas clouds to collapse to higher densities and fragment into smaller pieces, leading to the formation of lower-mass stars with longer lifetimes. This transition enabled the formation of stellar populations more similar to those we observe today, including stars like our Sun that can sustain nuclear burning for billions of years, timescales long enough for complex chemistry and potentially biology to develop on orbiting planets. The presence of heavy elements also made possible the formation of dust grains, which play crucial roles in cooling star-forming gas and providing the raw materials for terrestrial planet formation. Dr. Raffaella Schneider, an astrophysicist at the University of Rome, who studies the transition from population 3 to population 2 star formation, has developed models that trace how the first heavy elements influence subsequent stellar formation. Even tiny amounts of carbon and oxygen can dramatically change the cooling properties of star-forming gas, she explains, while showing calculations that demonstrate how heavy element abundances as low as 1,000th of the solar value can trigger a transition to lower-mass star formation. This transition was crucial for the development of planetary systems like our own. The first generation of stars was too massive and short-lived to provide stable environments for planet formation and biological evolution. Only when metal-enriched gas clouds began forming lower-mass, longer-lived stars did the universe develop the potential for complex chemistry and life. As we trace the cosmic story from the Dark Ages through the formation of the first stars and galaxies, we see how gravity, acting on tiny initial fluctuations, gradually built up the complex structures that fill today's universe. The first stars served as cosmic architects, transforming the pristine simplicity of the post-Big Bang universe into a cosmos rich with chemical complexity and structural diversity. This transformation was not gentle or gradual. It was driven by some of the most violent processes in nature, including stellar explosions that released more energy in seconds than our sun will produce over its entire 10 billion year lifetime. Yet from this violence emerged the elements that make planets, life, and consciousness possible, distributed throughout the cosmos by stellar winds and galactic outflows that continue to shape the chemical evolution of the universe today. The story of cosmic origins reminds us that we are intimately connected to the most dramatic chapters in the universe's history. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of ancient stars and distributed through space by stellar explosions that occurred billions of years before our solar system formed. We are, quite literally, made of star stuff, carrying within our bodies the elemental legacy of the universe's first generation of stellar architects. As we continue to push deeper into cosmic time with increasingly powerful telescopes and more sophisticated theoretical models, we uncover new details about these formative epochs and gain deeper appreciation for the complex processes that transformed a simple, uniform universe into the rich, structured cosmos we inhabit today. Now, we are moving to the next part of the documentary, where we witness how the cosmos matured from its violent infancy into the structured universe we observe today. This is the story of how gravity's patient architecture transformed scattered matter into the cosmic web that spans billions of light years, creating the framework upon which galaxies, stars, and ultimately life itself would emerge. Segment 4: The Cosmic Web of Mystery. After the universe's first billion years of stellar violence and chemical enrichment, a more subtle but equally profound transformation began to unfold. The random distribution of matter that characterized the early cosmos gradually gave way to an intricate network of structure-spanning scales, from individual galaxies to vast filaments stretching across hundreds of millions of light years. This cosmic web represents one of the most striking features of our universe, a pattern so regular and predictable that it reveals the fundamental forces governing cosmic evolution, yet so complex that we are only beginning to understand how it shapes the formation and fate of galaxies. The story of this cosmic architecture begins with a remarkable discovery made in 1965 by two Bell Laboratory engineers who were trying to eliminate an annoying source of static from their radio antenna. Arno Penzias and Robert Wilson had been tasked with preparing a horn-shaped antenna for satellite communications, but they encountered a persistent background noise that seemed to come from every direction in the sky. After ruling out terrestrial sources, including famously cleaning pigeon droppings from their equipment, they realized they had detected something far more significant: the cosmic microwave background radiation, the afterglow of the Big Bang itself. Dr. David Wilkinson, who was part of the Princeton team that confirmed the cosmic significance of this discovery, reflects on the moment when they realized what Penzias and Wilson had found. "We had been building our own instrument to search for this background radiation based on theoretical predictions," he recalls while standing next to a replica of the original horn antenna. "When we learned about the Bell Labs detection, we knew immediately that this was the smoking gun evidence for the Big Bang theory. Here was direct observational proof that the universe had once been in a hot, dense state and had been cooling ever since. But the cosmic microwave background revealed far more than just evidence for the Big Bang. Detailed measurements of this ancient light showed that it was not perfectly uniform. it contained tiny temperature fluctuations of just a few parts in 100,000. These minute variations represented the seeds from which all cosmic structure would eventually grow, imprinted on the universe when it was only 380,000 years old and first became transparent to light. The Cosmic Background Explorer satellite, launched in 1989, provided the first detailed maps of these primordial fluctuations. Dr. George Smoot, who led the mission's analysis, describes the significance of what they observed. "We were seeing the universe as it was when atoms first formed and the cosmic fog lifted," he explains, while examining the famous COBE sky maps that show variations in the background temperature. These tiny ripples in the afterglow of creation contained all the information needed to predict where galaxies would form billions of years later. The pattern revealed by COBE showed fluctuations on the largest observable scales, but higher resolution was needed to understand how these primordial seeds evolved into the complex structures we see today. The Wilkinson Microwave Anisotropy Probe, launched in 2001, provided unprecedented detail about these early fluctuations, measuring temperature variations across the sky with precision sufficient to test fundamental theories about cosmic evolution. Dr. Lyman Page, a Princeton physicist who worked on both WMAP and its successor, the Planck satellite, explains how these observations revolutionized cosmology. The cosmic microwave background acts like a baby picture of the universe, he says, while showing detailed maps that reveal the statistical properties of primordial fluctuations. By analyzing the size, strength, and distribution of these temperature variations, we can determine fundamental parameters like the age of the universe, its geometry, and the relative amounts of ordinary matter, dark matter, and dark energy. These measurements revealed that ordinary matter, the atoms that make up stars, planets, and everything we can directly observe, comprises less than 5% of the universe's total energy density. Dark matter, which interacts gravitationally but remains invisible to electromagnetic radiation, accounts for about 27%, while the mysterious dark energy that drives cosmic acceleration makes up the remaining 68%. This cosmic census fundamentally changed our understanding of what the universe is made of and how it evolves. But understanding the ingredients of the universe is only the beginning of comprehending cosmic structure formation. To trace how tiny primordial fluctuations grew into the cosmic web requires following the complex interplay between dark matter, ordinary matter, and the expanding spacetime backdrop over billions of years of cosmic history. Dr. Carlos Frank, a cosmologist at Durham University, who pioneered large-scale computer simulations of structure formation, leads visitors through a visualization center where massive computational models reveal the evolution of cosmic structure. Dark matter provides the gravitational scaffolding upon which all visible structure forms, he explains, while manipulating three-dimensional renderings that show how matter clumps and flows over cosmic time. Because dark matter particles interact only gravitationally, they begin clumping together as soon as the universe becomes matter-dominated, about 50,000 years after the Big Bang. The simulations reveal a universe that evolves like a vast gravitational symphony. Initially, smooth distributions of dark matter develop tiny density enhancements that grow through gravitational attraction. These small perturbations merge and consolidate, forming increasingly massive structures through a hierarchical process that continues throughout cosmic history. Small dark matter halos merge to form larger ones, which eventually become the hosts for individual galaxies and galaxy clusters. But the evolution of ordinary matter follows a more complex path. Unlike dark matter, ordinary matter can radiate away energy through electromagnetic processes, allowing it to cool and condense within dark matter halos. This cooling enables the formation of the first stars and galaxies, which then begin to influence their surroundings through stellar winds, supernova explosions, and radiation from actively accreting black holes. Dr. Romil Dave, a computational astrophysicist who develops simulations that include these complex feedback processes, describes the challenge of modeling realistic galaxy formation. You can't just simulate the dark matter and expect to understand how galaxies form. He explains, while showing comparisons between dark matter-only simulations and those that include gas physics and stellar feedback. The formation of stars changes everything. It heats the surrounding gas, drives powerful outflows, and fundamentally alters how matter accumulates in dark matter halos. The most sophisticated modern simulations, such as the Illustris and Eagle projects, follow the evolution of both dark and ordinary matter across cosmic time, tracking processes from the largest scales down to individual galaxies. These simulations reproduce many observed properties of the galaxy population, including the relationship between galaxy mass and stellar content, the morphological diversity of galaxy types, and the statistical properties of the cosmic web. But observations of the real universe continue to reveal phenomena that challenge our theoretical understanding. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey and its successors, have mapped the three-dimensional distribution of galaxies across billions of light years, revealing the detailed structure of the cosmic web with unprecedented clarity. Dr. Michael Strauss, an observational cosmologist who has worked on several major galaxy surveys, stands before a wall-sized display showing the three-dimensional distribution of over 1 million galaxies. What we see is a universe organized into a vast network of filaments, sheets, and voids, he explains, while highlighting features that span hundreds of millions of light years. Galaxies are not randomly distributed. They trace out a cosmic web that extends across the entire observable universe. The cosmic web consists of several distinct components. Dense nodes, where filaments intersect, contain rich galaxy clusters. Gravitationally bound systems containing hundreds or thousands of galaxies embedded in hot, X-ray emitting gas. Filamentary structures connect these clusters, channeling matter and galaxies along preferred directions. Sheet-like walls contain most galaxies in the universe, while vast cosmic voids, regions largely empty of galaxies, occupy most of the universe's volume. This web-like structure reflects the gravitational amplification of primordial density fluctuations, but its detailed properties depend on complex physics involving dark matter, dark energy, and the feedback processes that regulate galaxy formation. Understanding how these components work together requires combining theoretical modeling, numerical simulations, and increasingly sophisticated observations. Recent discoveries have added new layers of mystery to cosmic web studies. Observations suggest that a significant fraction of ordinary matter remains missing, the missing baryon problem, with much of it likely residing in warm, diffuse gas within cosmic filaments that is difficult to detect directly. Advanced X-ray and radio telescopes are beginning to trace this hidden component, revealing the full extent of the cosmic web's gaseous content. Dr. Hideki Tanimura, an astronomer who uses gravitational lensing and other techniques to study the cosmic web's invisible components, describes the challenge of detecting diffuse intergalactic gas. The majority of ordinary matter in the universe doesn't shine. It exists as warm plasma in the spaces between galaxies, he explains, while showing maps that reveal the subtle signatures of this hidden material. We're developing new techniques to trace this missing matter and understand how it flows through the cosmic web. The cosmic web also provides crucial insights into the nature of dark energy, the mysterious component that drives the accelerating expansion of the universe. By measuring how the cosmic web's structure has evolved over time, astronomers can test different models of dark energy and constrain its properties. Dr. Nikhil Padmanabhan, a cosmologist at Yale University who uses large-scale structure to study dark energy, explains how galaxy surveys provide unique probes of cosmic acceleration. The cosmic web acts like a fossil record of cosmic expansion, he says, while showing measurements of how the characteristic scale of cosmic structure has evolved over billions of years. By measuring distances to galaxies at different epochs, we can reconstruct the expansion history of the universe and test whether dark energy has changed over time. Upcoming surveys, such as the Dark Energy Spectroscopic Instrument and the Vera Rubin Observatory, will map the cosmic web with unprecedented precision, measuring distances to tens of millions of galaxies and tracing the evolution of cosmic structure across most of the universe's history. These observations will provide the most stringent tests yet of our understanding of dark matter, dark energy, and the physics governing cosmic structure formation. But the cosmic web is not just a static pattern. It represents an active, evolving environment that continues to shape galaxy formation and evolution today. Gas flows through filamentary structures, feeding star formation in galaxies, while hot feedback from stellar processes and black hole activity redistributes matter throughout the web. Galaxy mergers, triggered by the web's gravitational dynamics, build up massive galaxies and drive the evolution of galaxy morphology. As we trace the evolution from primordial quantum fluctuations to the cosmic web we observe today, we see how gravity's patient architecture has organized matter across the largest scales while enabling the complex physics that govern star formation, galaxy evolution, and ultimately the emergence of planetary systems capable of supporting life. The cosmic web represents both the largest scale structure in the universe and the environmental framework within which all smaller scale phenomena occur. Understanding this vast network of matter and energy requires pushing the boundaries of both theoretical physics and observational astronomy, combining insights from quantum mechanics, general relativity, thermodynamics, and nuclear physics to comprehend how the universe has evolved from its simple beginnings into the complex structured cosmos we inhabit today. The cosmic web stands as testimony to the universe's remarkable ability to transform simple initial conditions into patterns of staggering beauty and complexity through the relentless action of fundamental physical laws. Now we are moving to the next part of the documentary, where we turn our attention to our own cosmic neighborhood and the hidden mysteries that lurk right here in our galactic backyard. While we've journeyed to the most distant reaches of the observable universe and peered back to the dawn of time itself, some of the most profound cosmic puzzles exist much closer to home, within our own Milky Way galaxy, and even within our solar system. Segment 5: Mysteries in our cosmic backyard. For centuries, humans have gazed up at the night sky, and marveled at the seemingly peaceful canopy of stars that stretches overhead. The Milky Way appears as a gentle river of light flowing across the heavens, while planets wander serenely among the constellations, following predictable paths that ancient astronomers could chart and predict. Yet this serene appearance masks a cosmos in constant violent motion, where invisible forces wage cosmic battles and mysterious phenomena unfold on scales both intimate and immense. Our galaxy, the Milky Way, is far from the stable, unchanging structure it appears to be from our earthbound perspective. Instead, it is a dynamic, evolving system containing over 100 billion stars, vast clouds of gas and dust, and dominated by invisible dark matter that outweighs all the visible material by a factor of 10 to 1. At its very center lurks a supermassive black hole containing 4 million times the mass of our Sun, actively consuming material and occasionally erupting with energy that dwarfs the combined output of billions of stars. Dr. Andrea Ghez stands atop Mauna Kea, Hawaii, where the twin Keck telescopes peer through the thin atmosphere into the heart of our galaxy. For over 2 decades, she has been tracking the motions of individual stars orbiting the galactic center, using these stellar dancers to map the invisible gravitational field of the monster black hole that dominates the innermost region of the Milky Way. When we first began this project, we had no idea what we would find, Dr. Ghez reflects, while adjusting the telescope's adaptive optics system that compensates for atmospheric turbulence. The stars closest to the galactic center are moving at speeds of thousands of kilometers per second, faster than we had ever seen stars move anywhere in the universe. Through decades of patient observation, her team has traced the elliptical orbits of stars that swing as close as 120 astronomical units from the black hole. Closer than Pluto's orbit around our Sun, these observations provide direct evidence not only for the black hole's existence, but for the bizarre predictions of Einstein's general relativity in the strongest gravitational field ever observed. When these stars reach their closest approach to the black hole, their light is stretched to longer wavelengths by the intense gravitational field, exactly as Einstein's equations predict. But the supermassive black hole at the center of our galaxy represents just one of countless mysteries hidden within our cosmic neighborhood. Recent observations have revealed that the Milky Way is surrounded by a vast halo of dark matter extending far beyond the visible stellar disk, containing streams and clumps of invisible material whose origins remain completely unknown. Some of these dark matter structures appear to be the remnants of smaller galaxies that were torn apart by tidal forces as they fell into the Milky Way's gravitational well, leaving behind ghostly traces of their former existence. Dr. Katherine Johnston, an astronomer at Columbia University who studies galactic archaeology, has developed sophisticated computer models to trace the assembly history of our galaxy by analyzing the positions and motions of stars throughout the Milky Way. Every star in our galaxy carries information about where it formed and how it got to its current location, she explains, while showing visualizations that reveal the complex streams and structures hidden within the stellar halo. By mapping these stellar populations, we can reconstruct the merger history of our galaxy and understand how it grew from a small collection of gas clouds into the massive spiral structure we see today. These studies have revealed that the Milky Way has been shaped by a series of violent encounters with smaller galaxies throughout its history. The largest of these events, known as the Gaia-Enceladus merger, occurred about 10 billion years ago, when a galaxy roughly 1/4 the mass of the early Milky Way collided with our galactic ancestor. This collision scattered stars throughout the galactic halo and may have triggered intense bursts of star formation that helped build the thick disk component of our galaxy. Even more dramatic events may be in store for our galactic future. The Andromeda Galaxy, our nearest large galactic neighbor, is currently approaching the Milky Way at a speed of 250,000 miles per hour and will collide with our galaxy in approximately 4.5 billion years. Computer simulations of this cosmic collision reveal a complex dance of gravitational forces that will completely restructure both galaxies, ultimately merging them into a single elliptical system that astronomers have dubbed Milkomeda. But galactic mysteries extend beyond these large-scale structural questions to encompass phenomena that challenge our understanding of fundamental physics. Throughout the Milky Way, astronomers have detected mysterious bursts of high-energy gamma rays emanating from sources that remain completely unidentified. These gamma-ray bursts release more energy in seconds than our sun will produce in its entire 10 billion year lifetime. Yet their origins are so poorly understood that they represent one of the greatest unsolved puzzles in modern astrophysics. Dr. Julie McInerney, a gamma-ray astronomer at NASA's Goddard Space Flight Center, leads observations with the Fermi Gamma-Ray Space Telescope, which has detected thousands of these enigmatic high-energy sources throughout our galaxy and beyond. Gamma rays are the most energetic form of electromagnetic radiation, she explains, while examining data from the telescope's latest observations. They're produced only in the most extreme environments in the universe, near black holes, in the aftermath of stellar explosions, or through processes involving the most exotic forms of matter and energy. Some of these gamma-ray sources have been identified with known astronomical objects, such as pulsars, the rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. But many others remain completely mysterious, with no visible counterparts at any other wavelength of light. These unidentified gamma-ray sources could represent entirely new classes of astronomical phenomena, or they might be signatures of dark matter particles annihilating each other in the galactic halo, a process that would provide the first direct detection of the mysterious substance that dominates the mass of our galaxy. Even our own solar system harbors profound mysteries that challenge our understanding of planetary formation and evolution. The recent discovery of the Kuiper Belt, a vast region of icy bodies beyond Neptune's orbit, has revealed that our solar system extends much farther into space than previously imagined and contains thousands of objects that preserve pristine records of conditions during the solar system's formation 4.6 billion years ago. Dr. Alan Stern, principal investigator of the New Horizons mission to Pluto, describes the revolutionary insights that have emerged from exploring these distant worlds. When New Horizons flew past Pluto in 2015, we expected to find a cold, dead world covered in ancient impact craters, he recalls, while examining high-resolution images that reveal Pluto's unexpectedly complex surface. Instead, we discovered a geologically active planet with flowing nitrogen glaciers, towering mountains made of water ice, and a complex atmosphere that changes dramatically with the seasons. These discoveries have forced astronomers to reconsider fundamental assumptions about planetary formation and the conditions necessary for geological activity. Pluto's moon cairn shows evidence of past tectonic activity despite being smaller than Earth's moon. while other Kuiper Belt objects display a remarkable diversity of sizes, shapes, and compositions that reflect the chaotic processes that shaped the outer solar system billions of years ago. But perhaps the most intriguing mystery within our solar system involves the possibility of life existing in environments that were previously thought to be completely inhospitable. Jupiter's moon. Europa harbors a vast ocean beneath its icy surface that contains more liquid water than all of Earth's oceans combined. Saturn's moon. Enceladus shoots geysers of water vapor into space from fractures in its south polar region, providing direct evidence of hydrothermal activity on the ocean floor that could potentially support life. Dr. Kevin Hand, an astrobiologist at NASA's Jet Propulsion Laboratory, studies these ocean worlds and their potential for harboring life. Europa and Enceladus represent some of the most promising targets in our search for life beyond Earth. He explains, while showing images of the towering water plumes erupting from Enceladus's surface. These moons have had liquid oceans for billions of years. They receive energy from tidal heating as they orbit their giant planet hosts, and they contain all the basic chemical ingredients necessary for life as we know it. Future missions to these ocean worlds will carry sophisticated instruments designed to search for chemical signatures of biological activity. The Europa Clipper mission, scheduled to launch in the 2020s, will use radar to map the thickness of Europa's ice shell and analyze the composition of material ejected from the moon's subsurface ocean. Similar missions to Enceladus could sample the water plumes directly, searching for organic molecules and other biosignatures that might indicate the presence of microbial life. Even more mysterious are the recent discoveries of interstellar objects passing through our solar system. Visitors from other stellar systems that provide our first direct samples of material from beyond the sun's gravitational influence. The first such object, named Oumuamua, was discovered in 2017 and displayed such unusual properties that astronomers initially struggled to determine whether it was an asteroid or a comet. Its elongated shape, unlike any known solar system object, and its unexpected acceleration as it departed the inner solar system, raised questions about its composition and origin. Dr. Robert Warwick, the astronomer who first spotted Oumuamua using the Pan-STARRS telescope in Hawaii, describes the excitement and confusion that surrounded this discovery. When we first calculated Oumuamua's orbit, we realized immediately that it wasn't bound to our solar system, he recalls, while showing the trajectory that carried the object past Earth and back toward interstellar space. This was the first confirmed interstellar visitor we had ever detected, and its properties were unlike anything we had seen before. Subsequent observations revealed that Oumuamua was accelerating away from the sun faster than could be explained by gravity alone, suggesting either that it was outgassing like a comet or that it was being pushed by radiation pressure on an unusually reflective surface. Neither explanation fully accounts for all of the object's observed properties, leaving its true nature as one of the most intriguing mysteries in contemporary astronomy. The discovery of Oumuamua has sparked new efforts to detect and study other interstellar visitors, with estimates suggesting that similar objects pass through the inner solar system several times per year. These cosmic messengers carry information about planetary formation processes in other stellar systems and provide our first opportunity to study material that originated around other stars. As we survey the mysteries that exist within our own cosmic neighborhood, we're reminded that the universe's most profound puzzles don't always require us to peer across billions of light years of space or back to the earliest epochs of cosmic history. Sometimes the greatest mysteries lie hidden in plain sight, waiting to be discovered through careful observation and analysis of phenomena that occur right here in our galactic backyard. The supermassive black hole at the center of our galaxy, the streams of dark matter flowing through the galactic halo, the possibility of life in the subsurface oceans of icy moons, the enigmatic gamma-ray sources scattered throughout the Milky Way. All of these mysteries exist within our local cosmic environment, yet they challenge our understanding of physics, astronomy, and biology just as profoundly as the most distant phenomena in the observable universe. These local mysteries also remind us that our cosmic neighborhood is far from the peaceful, static environment it appears to be from our earthbound perspective. Instead, we inhabit a dynamic, evolving system where violent processes constantly reshape the structure of galaxies, where invisible forces dominate the motions of stars and planets, and where the potential for life may extend far beyond the narrow range of environments we once thought necessary for biological activity. As we continue to explore our cosmic backyard with increasingly sophisticated instruments and theoretical frameworks, we can expect to uncover new mysteries that will further challenge our understanding of the universe and our place within it. The cosmos holds its secrets close, revealing them only to those patient and persistent enough to search carefully in the most unexpected places. Now, we are moving to the next part of the documentary, where we descend into the Earth's deepest chambers and venture into the void of space to witness humanity's most ambitious hunt for the universe's most elusive quarry. We enter the realm of the invisible majority, the mysterious dark matter that outweighs everything we can see by a factor of 5 to 1, yet remains stubbornly hidden from every instrument science has devised to detect it. Segment 6. Journey into the invisible realm. 2 miles beneath the Black Hills of South Dakota, in tunnels carved from rock that formed when dinosaurs ruled the Earth, the most sensitive scientific instruments ever built wait in perfect darkness for a collision that may never come. Here, in the Sanford Underground Research Facility, teams of physicists have constructed detectors so exquisitely sensitive they can record the impact of a single subatomic particle hitting a xenon atom, releasing a flash of light dimmer than a single photon from a distant star. This is ground zero in humanity's hunt for dark matter, the invisible substance that astronomers believe comprises more than a quarter of everything that exists in the universe. Yet despite decades of increasingly sophisticated searches, these ghost particles continue to elude detection, forcing scientists to question fundamental assumptions about the nature of matter itself and pushing the boundaries of experimental physics to their absolute limits. Dr. Richard Gateskill stands in the heart of the LUX Zeppelin experiment, surrounded by tanks containing 7 tons of liquid xenon cooled to temperatures colder than outer space. The detector represents the culmination of decades of technological development designed to catch dark matter particles in the act of colliding with ordinary atoms. We're essentially trying to observe something that barely interacts with normal matter, Dr. Gateskill explains, while gesturing toward the massive detector that fills the underground cavern. Dark matter particles could be streaming through your body right now, billions of them every second, and you would feel absolutely nothing. The challenge facing dark matter hunters is unlike any other in experimental physics. Unlike neutrinos, which can be detected when they occasionally interact with atomic nuclei, Dark matter particles appear to interact with ordinary matter so rarely that catching even a single collision requires detectors containing tons of target material and years of patient observation. The detectors must be shielded from cosmic rays by miles of solid rock and surrounded by layers of ultra-pure materials to eliminate every possible source of background radiation that might mimic a dark matter signal. But the underground hunt represents just one approach in a global campaign to detect these elusive particles. High above the Earth's atmosphere, the Fermi Gamma Ray Space Telescope scans the cosmos, searching for telltale signatures of dark matter, particles annihilating with each other in regions where astronomical observations suggest dark matter is most concentrated. When dark matter particles collide with their antimatter counterparts, theory predicts they should produce bursts of high-energy gamma rays that space-based telescopes can detect. Dr. Julie McInerney, the Fermi Project scientist at NASA's Goddard Space Flight Center, describes the challenges of this indirect detection approach while examining data from the telescope's latest observations. We're looking for gamma-ray signals that are slightly brighter than what we would expect from known astrophysical sources, she explains, while pointing to maps showing gamma-ray emission from the center of the Milky Way. The difficulty is that there are many conventional sources of gamma rays: pulsars, black holes, supernova remnants that can produce signals similar to what we might expect from dark matter annihilation. The search has led astronomers to focus on dwarf galaxies, small collections of stars that appear to be dominated by dark matter yet contain relatively few conventional sources of gamma-ray emission. These cosmic laboratories provide cleaner environments for testing dark matter theories. But even here, the signals remain tantalizingly ambiguous. Several dwarf galaxies show gamma-ray emission that could potentially be explained by dark matter annihilation, but alternative explanations involving unknown populations of pulsars or other exotic objects cannot be ruled out. Meanwhile, particle physicists are attacking the problem from the opposite direction, using the world's most powerful particle accelerators to try to create dark matter particles in high-energy collisions. At CERN's Large Hadron Collider, protons are smashed together at energies approaching those that existed microseconds after the Big Bang, potentially producing exotic particles that exist only in the extreme conditions of the early universe. Dr. Sarah Demers, a particle physicist at Yale University who works on dark matter searches at the LHC, describes how these production experiments complement direct and indirect detection efforts. If dark matter particles can be produced in high-energy collisions, we should be able to create them in our accelerators, she explains, while examining data from billions of proton collisions. We look for events where some of the collision energy seems to disappear, carried away by invisible particles that escape our detectors without leaving any trace. The LHC experiments have set increasingly stringent limits on the properties of dark matter particles, ruling out many theoretical models while simultaneously suggesting that these particles may be even more exotic than previously imagined. Some theories propose that dark matter exists in a completely separate dark sector of physics, interacting with ordinary matter only through gravity and perhaps through new forces that operate only between dark matter particles. This possibility has led to the development of increasingly creative detection strategies. Dr. Andrei Derivianko, a theoretical physicist at the University of Nevada, has proposed using networks of atomic clocks to search for dark matter. His approach exploits the fact that if dark matter consists of very light particles with wavelengths comparable to the size of the solar system, these particles would create subtle oscillations in the fundamental constants of physics that could be detected by comparing precision measurements across vast distances. Atomic clocks are the most precise instruments humans have ever built, Dr. Derivianko explains, while showing calculations that demonstrate how dark matter waves might affect the frequencies of atomic transitions. By comparing the tick rates of atomic clocks separated by thousands of kilometers, we can search for dark matter particles that would be completely invisible to conventional detectors. This approach allows us to probe mass ranges that are inaccessible to underground experiments. Recent experiments using networks of atomic clocks connected by fiber optic cables have begun to constrain the properties of ultralight dark matter, demonstrating the power of precision measurement to probe fundamental physics. These searches complement astronomical observations that use the precise timing of pulsar signals to search for gravitational wave signatures that might be produced by dark matter interactions on galactic scales. But perhaps the most intriguing possibility is that dark matter might reveal itself through entirely unexpected phenomena that current theories have not anticipated. The history of physics is filled with discoveries that came from careful observation of anomalies that didn't fit existing theoretical frameworks. The discovery of dark matter itself emerged from astronomical observations that showed galaxies and galaxy clusters contain much more mass than can be accounted for by visible stars and gas. Dr. Vera Rubin's pioneering observations of galaxy rotation curves in the 1970s revealed that stars in the outer regions of galaxies are moving faster than they should if only visible matter were providing the gravitational force holding the galaxies together. This discovery, initially met with skepticism, has been confirmed by thousands of subsequent observations and has led to the inference that galaxies are embedded in massive halos of invisible dark matter. But the true nature of this dark matter remains one of the greatest unsolved problems in modern physics. Leading theoretical candidates include weakly interacting massive particles, WIMPs, axions, sterile neutrinos, and primordial black holes left over from the early universe. Each possibility requires different experimental approaches and makes different predictions about how dark matter might reveal itself through astronomical observations. Dr. Catherine Fries, a theoretical physicist at the University of Texas who has spent decades developing dark matter theories, reflects on the evolution of the field while reviewing the latest experimental results. When I started working on dark matter theory in the 1980s, we were optimistic that WIMP particles would be detected within a few years, she recalls, while examining data from the most recent underground experiments. The fact that we haven't found them yet either means they interact even more weakly with ordinary matter than we thought, or it means we need to consider entirely different types of dark matter particles. The absence of clear dark matter signals has led some physicists to propose alternative theories that modify our understanding of gravity rather than invoking invisible matter. Modified Newtonian dynamics, MOND, and other alternative gravity theories attempt to explain galactic rotation curves and other astronomical observations by changing the laws of physics rather than adding new forms of matter. However, these theories face their own challenges in explaining the full range of cosmological observations, particularly the patterns seen in the cosmic microwave background radiation. The search for dark matter has also revealed unexpected connections between particle physics and cosmology, driving the development of new theoretical frameworks that unify our understanding of the smallest and largest scales in the universe. String theory, extra-dimensional models, and supersymmetry all make specific predictions about dark matter particles that can be tested through both underground detectors and astronomical observations. As experimental sensitivity continues to improve, dark matter hunters are exploring increasingly exotic detection strategies. Some experiments search for dark matter particles that might get trapped inside the Earth or the Sun, accumulating over cosmic time and occasionally annihilating to produce detectable neutrino signals. Others look for seasonal variations in dark matter signals that would reflect the Earth's changing motion through the galactic dark matter halo as it orbits the Sun. The quest to detect dark matter has also driven remarkable advances in detector technology that have found applications far beyond fundamental physics research. Ultra-low noise electronics developed for dark matter experiments are being used in medical imaging devices, while the techniques for creating ultra-pure materials have applications in semiconductor manufacturing and quantum computing research. Yet perhaps the most profound impact of dark matter research lies in its potential to revolutionize our understanding of the universe's fundamental structure. The discovery and characterization of dark matter particles would provide crucial insights into the physics of the early universe, the formation of cosmic structures, and the ultimate fate of the cosmos. It might also reveal new fundamental forces or symmetries that could reshape our understanding of reality at its most basic level. Dr. Elena April, leader of the XENON collaboration, stands before the latest iteration of the experiment, a detector containing 8.3 tons of liquid xenon that represents the current state of the art in dark matter detection technology. "We're at a critical juncture in the field," she observes, while reviewing data from years of continuous operation. "Either we're on the verge of detecting dark matter particles with the next generation of experiments, or we need to fundamentally reconsider our assumptions about what dark matter actually is." The journey into the invisible realm continues to push the boundaries of human knowledge and technological capability. In underground laboratories around the world, in space-based telescopes scanning the gamma-ray sky, and in particle accelerators recreating the conditions of the early universe, thousands of scientists continue their patient hunt for the universe's most elusive component. Their work represents one of the greatest detective stories in the history of science. The attempt to unmask the invisible majority that shapes the cosmos, yet steadfastly refuses to reveal its true nature. As we probe deeper into this hidden realm, we're reminded that the universe is far stranger and more mysterious than our everyday experience suggests. The dark matter that flows invisibly through our bodies and fills the space between stars represents a form of reality that exists parallel to everything we can see and touch, yet remains almost entirely unknown to us. Understanding this invisible realm may ultimately prove to be the key to unlocking some of the universe's deepest secrets and revealing new aspects of the cosmic story that we have only begun to imagine. Now we are moving to the last part of the documentary. And first, I want to thank all of you for watching the Sleep Lab's journey through the deepest mysteries of our universe. Your curiosity and engagement drive us to explore these cosmic puzzles that have captivated humanity for generations. As we reach the conclusion of our cosmic odyssey, we find ourselves confronting perhaps the most profound question of all. What does our expanding understanding of the universe's mysteries tell us about our own place in this vast, incomprehensible cosmos? The eternal quest. Standing at the edge of human knowledge, gazing into the cosmic abyss that stretches beyond our comprehension, we realize that our journey through the universe's mysteries has brought us full circle to the most fundamental questions that have driven human curiosity since we first looked up at the night sky and wondered what lies beyond. Each mystery we have explored, from the invisible dark matter that flows through our bodies to the supermassive black holes that anchor galaxies, from the quantum fluctuations that gave birth to cosmic structure to the possibility of life in the subsurface oceans of distant moons, has revealed not just the strange and wonderful nature of the universe, but something profound about ourselves as conscious beings capable of contemplating our own cosmic significance. The hunt for answers that began in underground laboratories and mountaintop observatories has taken us on a journey that spans 13 billion years of cosmic history and extends across spatial scales from the subatomic realm to the largest structures in the observable universe. Along the way, we have discovered that the cosmos is far stranger, more violent, and more mysterious than our ancestors ever imagined. We have learned that the familiar world of atoms and molecules, planets and stars, galaxies and nebulae represents just the visible tip of a cosmic iceberg whose bulk remains hidden in realms of physics that challenge our most basic intuitions about the nature of reality. Dr. Neil deGrasse Tyson, standing beneath the dome of the Hayden Planetarium in New York, reflects on what our growing catalog of cosmic mysteries reveals about the human condition. Every time we solve one mystery about the universe, we discover 10 new questions we never knew how to ask, he observes, while gesturing toward a display showing the latest deep field images from space telescopes. This is not a failure of science. It's the greatest success we could hope for. Each answer we find opens doors to previously unimaginable realms of inquiry, expanding our awareness of how much we still don't know. The mysteries we have encountered in our journey remind us that we live in a universe that operates according to rules far more exotic than anything our everyday experience prepares us to understand. Quantum mechanics tells us that particles can exist in multiple states simultaneously until the moment we observe them, while general relativity reveals that massive objects literally warp the fabric of space and time. The combination of these theories predicts phenomena so bizarre that even their creators initially doubted their reality. Black holes, where time slows to a crawl, gravitational waves that stretch and compress space itself, and quantum entanglement that allows instantaneous correlations across arbitrary distances. Yet these same exotic principles that seem to violate common sense are also responsible for the existence of stars that cook the elements of life in their nuclear furnaces, galaxies that organize billions of stellar systems into vast rotating structures, and the cosmic web that spans hundreds of millions of light years and provides the scaffolding upon which all visible structure hangs. The universe's mysteries are not separate from its beauty. They are the source of that beauty, the hidden mechanisms that transform simple initial conditions into the rich, complex cosmos we inhabit today. Dr. Lisa Randall, a theoretical physicist at Harvard University who studies extra dimensions and the fundamental structure of reality, contemplates the implications of our cosmic discoveries while examining equations that describe how our three-dimensional reality might be embedded in a higher dimensional space. The universe doesn't care whether its operating principles are intuitive to creatures like us who evolved on the surface of one small planet, she explains, while pointing to mathematical frameworks that suggest reality might contain dimensions we cannot directly perceive. The fact that we can use our brains, arrangements of atoms that formed in stellar cores billions of years ago, to discover and understand these cosmic principles is perhaps the most remarkable mystery of all. This realization brings us to one of the deepest puzzles in all of science: the apparent fine-tuning of cosmic parameters that makes our existence possible. The masses of fundamental particles, the strengths of the basic forces, the rate of cosmic expansion, the density fluctuations that grew into galaxies, all of these seem to be set to precisely the values necessary for stars to form, heavy elements to be produced, and complex chemistry to develop over billions of years. Change any of these parameters by small amounts, and the universe becomes a place where stars never ignite, atoms never form, or space expands so rapidly that matter never clumps together into organized structures. Some physicists interpret this apparent fine-tuning as evidence for a multiverse, a vast ensemble of universes with different physical laws and cosmic parameters, of which we observe only one, because we can exist only in universes with properties that allow for the development of complexity and consciousness. In this view, our universe is not special, except for the fact that its parameters happen to be compatible with our existence. The apparent fine-tuning is simply a selection effect. We find ourselves in a universe that allows for our existence because we could not observe universes that do not. Dr. Max Tegmark, a cosmologist at MIT who studies the mathematical structure of reality, describes how this multiverse perspective changes our understanding of cosmic mysteries. If there are indeed multiple universes with different physical laws, then many of the mysteries we encounter in our universe, why the cosmological constant has the value it does, why space has 3 dimensions, why certain particles have the masses they do, might have straightforward anthropic explanations, he explains, while showing models that illustrate how different cosmic parameters lead to different types of universes. We observe these particular values not because they are somehow special or inevitable, but because they are the only values compatible with the existence of observers like us. But this multiverse hypothesis raises as many questions as it answers. If other universes exist with different physical laws, are there versions of reality where consciousness develops in forms we cannot imagine? Are there universes where the laws of physics are so different that the very concepts of space, time, and causality break down? And, perhaps most importantly, if we can never observe or interact with these other universes, in what sense can we say they exist at all? These questions push us to the boundaries of science itself, where empirical observation meets philosophical speculation, and where our understanding of cosmic mysteries blends with our deepest questions about the nature of existence, consciousness, and meaning. The universe revealed by modern astronomy and physics is simultaneously more vast and more intimate than previous generations could have imagined. Vast in its spatial and temporal scales, intimate in the way its most exotic phenomena are connected to our own existence through the cosmic processes that created the atoms in our bodies and the energy that powers our thoughts. Dr. Sean Carroll, a theoretical physicist at Caltech who studies cosmology and the arrow of time, reflects on how our growing understanding of cosmic mysteries changes our perspective on human significance. We are not the center of the universe in any spatial sense. We live on one planet orbiting one star in one galaxy among hundreds of billions, he observes, while examining data that traces the cosmic history from the Big Bang to the present day. But we may be central in a different sense. As far as we know, we are the only arrangements of matter in our cosmic neighborhood that have developed the ability to contemplate the universe's mysteries and seek answers to fundamental questions about reality itself. This perspective suggests that consciousness might play a more important role in the cosmic story than our scientific theories currently acknowledge. The fact that the universe has evolved structures complex enough to understand their own origins and contemplate their own nature represents a remarkable development in cosmic history. Through us, the universe has become aware of itself. A collection of atoms that was once scattered through interstellar space has organized itself into patterns that can perceive, think, and wonder about the cosmic processes that created them. The search for cosmic mysteries that began with our hunt for dark matter and black holes ultimately leads us back to the mystery of our own existence and our capacity to understand the universe around us. The same quantum mechanical principles that govern the behavior of subatomic particles also operate in the neural networks of our brains. The same gravitational forces that shape the largest structures in the cosmos also influence the flow of blood through our bodies. We are not separate from the cosmic mysteries we study. We are manifestations of them, temporary arrangements of cosmic matter that have developed the extraordinary ability to investigate their own origins. As we look toward the future, new generations of instruments will undoubtedly reveal additional cosmic mysteries that we cannot yet imagine. The James Webb Space Telescope is already detecting galaxies that formed when the universe was younger than we thought possible. Gravitational wave detectors are opening entirely new windows into the most violent processes in the cosmos. Underground dark matter experiments are pushing toward sensitivities that may finally reveal the nature of the invisible majority. Quantum computers are beginning to explore the fundamental limits of information processing in physical systems. Each of these investigations will likely raise new questions that challenge our current understanding and reveal additional layers of cosmic mystery. The universe has consistently proven more strange, more beautiful, and more mysterious than we expected, and there is every reason to believe this pattern will continue as we push deeper into previously unexplored territories of space, time, and physical law. But perhaps the most important lesson from our journey through cosmic mysteries is that the questions themselves are as valuable as the answers we seek. The human capacity to wonder, to ask why, and how, and what if, represents one of the most remarkable emergent properties in the known universe. In a cosmos dominated by dark matter and dark energy, where most of reality remains hidden from our direct perception, the fact that conscious observers have emerged who can contemplate these mysteries and gradually expand the boundaries of knowledge represents a kind of cosmic awakening. Dr. Carlo Rovelli, a theoretical physicist who studies the nature of time and space, offers a final reflection on what our cosmic odyssey reveals about the human condition. The universe is under no obligation to be comprehensible to us, yet it has proven surprisingly amenable to human understanding, he observes, while contemplating the mathematical equations that describe cosmic evolution. This suggests a deep connection between the structure of reality and the structure of conscious thought, a connection that may be one of the greatest mysteries we have yet to fully explore. As we conclude our journey through the mysteries of the universe, we return to where we began, gazing up at the night sky and wondering what lies beyond. But now, our sense of wonder is informed by knowledge of the extraordinary processes that created the stars, the invisible dark matter that shapes their motions, and the possibility that consciousness itself may play a fundamental role in the cosmic story. We have learned that the universe is both more strange and more beautiful than we imagined, and that our capacity to discover and understand these cosmic mysteries is itself perhaps the most remarkable mystery of all. The eternal quest to understand our cosmic home continues, driven by the same curiosity that led our ancestors to first wonder about the lights in the sky. As we push forward into new frontiers of knowledge, we carry with us the profound realization that we are not merely observers of cosmic mysteries. We are participants in them, products of cosmic evolution who have developed the extraordinary ability to contemplate our own origins and seek answers to questions that may be as infinite as the universe itself. Thank you for joining the Sleep Lab on this cosmic journey through the mysteries that define our universe. The quest for understanding continues, and each new discovery brings us closer to comprehending our place in the vast, beautiful, and eternally mysterious cosmos we call home. Keep wondering, keep questioning, and never stop looking up at the stars with the same sense of awe and curiosity that drives all scientific discovery. The universe is waiting for us to uncover its next great mystery.